Hey everyone, and welcome back to edritt. In this lecture, we are gonna study the introduction to digital electronics, where we are gonna see what are analog signals, what are their drawbacks, and what does this digital means, and then how do we convert these analog signals into the digital signals using the concept of sampling and quantization. So before jumping in, let's first try to understand some basics about digital electronics. Okay, so we have this digital electronics. Okay, in this digital electronics, we have this word called digital, right? Now, from where this word comes from? This comes from a word which we call as digits. Okay. Now, what does this digits means? This digit means the number of symbols. Let's try to understand this through an example. So if I take a simple example of alphabets, right? In alphabets, we know there are totally 26 symbols. And what are those symbols? Those symbols are A, B, C, D, up to Z, right? Similarly, if I take another example, I can take an example of number system. Okay. So this number system we will later call as decimal number system, which is normal human readable number system or human understandable number system. We know that this has in total 10 symbols, right? This has in total 10 symbols. And what are those symbols? Those symbols are 0, 1, 2, 3, up to 9, right? Now, if you see both of these examples, or let us take one another example of binary number system. Okay? This will understand in deep in the further coming lectures. In binary number systems, we have only two symbols available. Okay, and those symbols are 0 and 1. Now, if you see all of these examples, okay, in all of these examples, the number of symbols were finite, right? So due to this fact, what we can say is we on in digital we only have finite number of possibilities. Okay, but why we are focusing on this word? Let's try to understand this through the analog signal. Okay, so we'll try to understand what does analog means. Okay, so when I say analog, this comes from the word which we call as analogous. Now this analogous basically means similar. Okay, so similar means, the current value is pretty much similar to the previous value or the next value. It's not directly changing. Let me try to give you an example so that you can understand it better. So in this example, we are going to take a natural sine wave, which is available in nature. Okay. So this is a natural sine wave, which is available in nature. Now, if you take this point of interest, if you take this point of interest and then you take a pretty much nearer point and a pretty much previous nearer point. Okay. Now I will say this point as, let's say I'll say this point as T naught and I'll say this point as T naught plus delta and I'll say this point as T naught minus delta. Now the value of delta is tending to 0, which means it's nothing, right? Now if you see that, don't you think that this point and this point both are same? I mean, almost same we can say, right? So this is what analog means. So the same we can say is that, if I take this axis as my y axis and this axis as my x axis, generally we call it as time axis in signals and system, and this as amplitude axis. So if we take x and y axis, the signal is continuous. Continuous means non-breaking, right? The signal is continuous in both x and y axis. Okay. Now, point to note is that all the real world signals are analog in nature. Now just assume a scenario where I have a point t naught, which is, this x-axis I'll represent as time axis for the time being. Now assume a scenario where I have this value t naught, and this t naught also, this y can be any value, it can go up to any decimal point. Now this time axis can also have infinite number of possibilities, right? Because I can grab infinite number of time instances from this curve. So do you think it is feasible or possible to store this into a limited memory, which is digital memories? We'll come to that point. What does that digital means? But do you think it is really possible to store something infinite into a finite? No, right? This is why we use digital electronics, so that we can store this infinite amount of memory into a finite amount of storage. So the concluding point to note is the drawback with the analog signal. So the drawback is simply the memory required is infinite. Okay. So not possible to store, you know, this is the drawback of analog signal. Now, how can we store this information, at least the relevant information, somewhere so that we can use it and we can process it for something? This is where the concept of conversion from analog to digital comes in picture. So analog to digital conversion is something which you have to do. Okay. So how do we do the analog to digital conversion? So for that, what we do is, whatever analog signal we have, so I have this analog signal coming in. What do I do is, I simply, this analog signal, I pass it through something called as sampler, which samples different instances of time. What it is, we'll see about that in some time. Once I have that, I have the signal which I get is discrete time signal. And then once I have this discrete time signal, I do further approximation, and basically I pass it through quantizer. Okay. So this do the amplitude approximation. Okay. Once I'm done with this, what I get on the output is a digital signal. The digital signal which you can further process to use, whether to save or, process or whatever you want to do with that. Now let's try to understand the sampling and the process of quantization one by one. First, we'll try to understand the concept of sampling. Okay. What does this sampling means? It simply means, sample it different time intervals, or I should say sample value or amplitude of signal at different time intervals. Okay. Let's take the example of the sine wave. So this is my sine wave. Mhm. In this sine wave, this is my amplitude axis. I'll call it as xt, and this is my time axis. I'll call it as t. What I'll do is, I'll simply sample the values at different time instances. Okay. So this time instance which we select is something we call as sampling rate and denote it as TS. TS means the sampling interval. Okay. Basically the interval over which you are sampling the signal, the amplitude of the signal, and we have this Fs which is 1 by Ts. This is something we call as sampling rate. This just introduction, we'll read about it in details in the further coming lectures. Okay. So this sampling interval is something where I'll be collecting the value of the signal. So let's say at 0 instance, I'll collect the value, and then at TS instance, I'll collect the value. At TS instance, I'll collect the value. At 2 TS instance, I'll collect the value. At 3ts instance, I'll collect the value at 4ts instance, at 5ts instance, at 6ts instance, and then 7ts, 8ts, 9ts, 10ts, and so on. Okay. So on. Okay. So let's denote these numbers as ts, 2ts, 3ts, 4ts, 5ts, and so on. Okay. So at these points, I'll be sampling the values, or the sampling of the amplitude is something which I'll be doing. Now, if you see that, doesn't this convert to a discrete time signal? So, I mean, if I try to draw this diagram again, only with the sampled values, do you think this will look something like this? I am again taking this sine wave. Mhm. Oh, not- I'll simply grab these samples. So this is something, it will look like this. So one sample over here, then one sample over here, then one sample over here, and then one sample over here, and then one sample over here, one sample over here, one sample over here, and one sample over here, one sample over here, and so on. So this is something which we'll call as discrete time signal, because amplitude is still continuous, but the time axis is discrete. The value is not present over here, not present, right? The value is only present at TS, 2TS, 3TS, 4TS, 5TS, and so on. So value present at this 4TS, actually I should say at NTS, where N belongs to integer, right? So this is something we call as discrete time signal. Basically, they are discrete in time, but they are continuous in amplitude axis. Now, let's take this example. Like, let's look at this. So this final amplitude is almost one. It is one basically, because this is a sine wave, right? Xt is equal to sine t. Now take this point, you know, what this point can contain value. Let's say I'm saying this as x of 2ts. Mhm. So this x of 2ts can have a value between 0 to 1. Any value between 0 to 1. Can it be 0 0.1? Yes. Can it be 0.11? Yes. Can it be 0.111? Yes. Can it be 0.111111 up to infinite times 1? Yes, it can be. So don't you think that even though I have discretized my time axis, which means I only need to store the value of time axis at some certain points in my digital memory. Do you really think I can store this information, this infinite amount of information into the memory? No, right? That's where the concept of truncation comes in. Yeah. So that truncation means we'll round off the value. We'll chop down the other values and we'll round off the value depending on how much truncation we want to do. So this is where we'll use the concept of quantization. Okay. Basically, what is quantization? Very simple. Just like you know, uh, did the sampling interval only sampled at specific instances of time. Similarly, amplitude also, axis also, we will discretize so that we have only finite number of levels. So what we will do is, let's jump into the concept of quantization. So in the concept of quantization, what do we say is, we say that we will have the levels of approximations, levels of, and by what we decide these levels of approximation, that is something we decide by step size. Okay. And that step size is decided based on del. Okay. I mean, this is represented as del. So representation is del. So basically it tells the gap between two quantized levels. So this tells the gap between two quantized levels. Let me take you again to the amplitude axis. So assume that we have right now at this point we have this amplitude axis, okay, and we are gonna define the quantized levels over here. So what I can do is I can have quantized level below for the negative axis and the quantized level above for the positive axis. So one quantized level will be this axis only, which I'm representing as 0 volt. Okay, and then further quantization levels I can define like this. So zero, I'm gonna take the step size in this example as 0.5 volt. Okay, so as the step size is 0.5 volt, this value will be 0.5 volt, and then the next value it will be 1 volt. This value will be 1.5 volt. This value will be 2 volt, and then below we will have minus 0.5 volt, minus 1 volt, minus 1.5 volt. Okay, so this is something I'll call as 0.5 volt, 1.0 volt, 1.5 volt, and 2.0 volt. And here I'll call as minus 0.5 volt, minus 1.0 volt, minus 1.5 volt. Now we'll take the example which we took over here and we'll try to use the concept of quantization to map these things. Yeah. So I take this example and I'll put it over here, and what I will do is I'll define some quantization levels, you know, similar to this example. Okay. So just considering I'm defining the quantization levels, let's say these levels I'll represent by green. So assume this is my first level, this is my second level, this is my third level, and assume that this one is my fourth level. And below again, I have first level. Okay. By the way, this is also in level. 0 volt is also in level. I have my second level and assume that this is my third level. Okay. Now look at this value. Is this value closer to this level or this level? This is closer to this level, right? So we will have the sampled and quantized signal, something like this. I mean, the sampled value will be at TS and it will be quantized at this point. Now look at the signal. Is this closer to this one or this one? It seems to both, right? We'll consider this case, what happens in this case. Now for the timing, it assumes that this will go near to this one, this quantized level. Now look at this signal. Is this closer to this one or this one? Yeah, it is closer to this one. So this quantized level will go over here. This one is closer to this, so the quantized level will go over here. This one is also closer to this. This one is closer to zero axis itself. This one is closer to this one. This one is closer to this one. This one is closer to this one. Now I have, with the concept of sampling, actually I should write it over here. With the concept of sampling plus quantization, I have finite number of samples and finite info about the amplitude. As both things are finite, do you think that we can store this in digital memories, which is also finite? Both are finite, right? Yes, we can store it. So, so this way, so this way we can store, this way we can store finite information into finite memory. This is something which will convert the signal. There is one more step. I mean, there's more thing over here, but we won't discuss it over here to not confuse the reader. We'll come through it in the later parts of the lecture. But this is how we convert an analog signal into a digital signal. Yeah. There's one concept left, right? This specific point of interest where the quantization level was near to both of them. We'll try to discuss this in the quantization error concept. Let's try to understand what is that. So I have this concept of quantization error. What is this quantization error? Let's take an example number one. So we were taking sine wave, right? So in sine wave, let's take an example where the actual value is 0.60. The value of that signal is 0.60. And I have the step size. Firstly, I have the step size del, which is equal to step size. So this del value is equal to 0.5 volt. Okay. So I have this step size in 0.5 volt. So the possible values are 0 volt, 0.5 volt, 1 volt, and minus 1, minus 0.5 volt and minus 1 volt. Okay. For the sine wave. Now this 0.6 volt, what do you think will have the quantization level of? Will it be 0.5 volt or will it be 1 volt? It is near to 0.5 volt, right? Pretty obvious. So this will approximate to 0.5. Now just tell me what will be the quantization error in this case. The quantization error will be 0.6 minus 0.5, that comes up as 0.1 volt. This is something we call as the quantization error. Let's see another example. 0.85 volt. What do you think it will quantize to? Whether it will quantize to 0.5 or it will quantize to 1.0 volt. Obviously, it will quantize to 1.0 volt, right? Because that is more near to 0.85. So what would be the quantization error value? That will be mode of 0.85 minus 1.0. That comes up as 0.15. So this 0.15 is my quantization error in this case. Now, assume a scenario where the value is residing exactly at the mid of both the levels, right? This level and this level. This is one example. What could be the best case of quantization level? So this del is step size, right? This is the value, the difference between the two quantization levels, right? So can I say that the maximum quantization error can go when the value is residing in between of both, which is basically del by 2, the difference of del by 2. Let's take this example itself, 0.5 and 1 volt. So what is the average of 0.5 volt and 1 volt? So 0.5 plus 1.0 volt by 2, it gives me 0.75. Tell me where it can quantize. It can either quantize to 0.5 volt, it can either quantize to 1.0 volt. Don't you think so? In case of 0.5 volt, what is the quantization error? That value is 0.25. And in case of 1.0 as well, what is the quantized value? That also is 0.25. It can take any value, right? Now what value it will actually take? Because it is digital, we have only finite possibility. That is something which we will see in the further lectures. Okay. But the point to note is the maximum quantization error can be equal to del by 2. This is something which is a point to note. Now, you see, this quantization error depends on the step size. So if you increase the step size, the quantization error decreases. If you decrease the step size, the quantization error increases. But what it will do is it will have more levels of quantization, which means it will consume higher memory to store. So that is a drawback. Okay. So the more quantization levels you want, the more memory it will consume. The lesser the step size, the more the quantization levels, the more the memory it requires. Okay. Now let's see in another example. Sorry, let's move to the advantages of using a digital system over an analog system. Okay. So advantages of using digital system over analog system. Okay, we'll see some advantages of using digital system to analog system. First of all, let's try to understand how we use analog signals, use them, process them, and then finally give that to end user or the observer. Okay, so I'll try to explain that through an example. Okay. Just see this example. In this example, I'm gonna feed an analog signal. Okay, I'm gonna feed an analog signal. Now this analog signal is something I cannot play around with or I cannot store, right? So I first need to convert it into digital signal so that I can use it for some processing, playing around, either saving it or maybe doing some processing, digital processing. What processing we'll see in the further lectures. Okay. So what I'll do is I'll convert this analog signal into digital domain with something called as analog to digital converter. Once I have this digital signal over here, now this analog to digital converter is nothing but something which will try to do the sampling and quantization of the signal so that it can be converted into a digital signal. Once I have this digital signal, I'll play around with this with some processing. Now I don't know what this processing is for the time being, but I'll play around with that. Once I'm done with this play around, I need to show it to the observer, a real world observer, right? I cannot show these binary numbers to an observer. So I need to convert these binary numbers back to the actual numbers, right? The actual signal, which is actually analog, right? So what I'll do is I'll convert this digital, which is binary number, the random zeros and ones for an observer to a digital to the analog signal using something called as digital to analog converter. Now the definition of DAC and ADC is pretty much complex than it looks like over here. We'll try to understand that also in the further coming lectures. But once we convert it into analog domain, this is something which we will show to the observer. Okay, so this is my pretty nice observer. Now, what are the advantages of doing that? You know, so the advantages are basically first thing is these digital systems are easier to design. Second thing is these digital systems are less prone to noise than analog. Because why? Because analog has more granularity of the signal, while digital don't. It has sample and quantization levels basically. So these digital signals are less prone to noise, you know. So because they are, and the precision and the accuracy is also high. Precision and accuracy is also high. Okay. And then the third thing is using microprocessors and microcontrollers, we can implement our system in software. The best thing to do, write complex software, use the hardware to do all that complex processing. And then lastly, the information storage, which is the very first thing which we discuss. Information storage is easy. Okay, information storage is easy. These are the advantages of digital system. not limited to all these. There are more, but this is something which you should always remember if you are reading about digital electronics. So this is all for today's lecture. In the further lectures, we'll start studying about number systems, where we will first jump in to understand the radix of a number system and different available number systems with different radixes like binary, decimal, octal, and hexadecimal. And we'll deep dive into those things. What are different operations available? What are different things available? How to convert one to another? How to use one? Where to use one? Etc. etc. So thank you for watching this video. I hope to see you in the next one. Bye bye.